Okay, so finally, moving on to the last configuration, which is RAID level 5 or RAID-5. Okay, so it's also called block interleaved distributed parity, where it tries, instead of having a single disk solely used for storing parity data, which was done by RAID-4, instead in RAID-5, it interleave and rotate the parity data, the parity chunks, among all the disks that are involved and configured by RAID-5. So this is high-level idea of RAID-5. So let's further take how to basically rotate the parity across all the disks. So in RAID-5, in this example, RAID-5 configures 5 disks from disk 0 to disk 4. Unlike RAID-4, which uses disk 4 solely as a parity disk, instead in RAID-5, it kind of spread this whole parity chunks out across among all the disks involved, all the disks configured. In this example, it also kind of rotate the disks at different stripe levels. So this is the stripe. Okay, so the parity for first stripe stored under offset 0, and the parity data for the second stripe stored at disk 3, and you basically apply the same strategy for the third for offset number 2. So this is offset number 1. For offset number 2, the parity data, the parity chunk is stored at disk number 2. And the same for P3 and P4. You basically use this policy to implement this kind of rotating parity kind of mechanism, okay? So, RAID-5 works at a very high level, almost identically the same as RAID-4, but except that the fact that it rotates a parity disk, the parity data block across all drives. And this fact and this subtle difference, it actually makes a small impact on the performance metric, as will be shown in the next couple of slides when we come down to the performance analysis of RAID-5. So let's see how exactly it's different. Okay, so the rest of the analysis, the metrics are almost identical, exactly the same as RAID-4. So in terms of, so RAID-4, same capacity, the same reliability level, and the same random read and random write latency, okay? The only difference is the throughput. In fact, RAID-5 configuration improves a little bit for throughput. Why is that? It's because, especially for the random read and random write, these two, okay? For random read, it's in fact n times r, because it effectively rotates and spread this whole parity chunks to all of the disks. That means instead of employing one single disk solely for storing parity chunks, each one of these n disks, or specifically 5 disks, can be used to contribute to the random read, serving random read operations. So that is why it's n times r. But this is for random read. For random writes, why we have this question? So how to analyze the random write operations, the performance, the throughput of random writes. So let's say we have a 5-disk RAID-5 configuration. How much random write throughput it could sustain effectively. So next, let's take a look at one example, which provides, effectively illustrate this reasoning and this analysis. Okay, so instead of talking about multiple concurrently issued random writes, let's focus on 2 outstanding random writes. So the first write operation, so right now here, this is a logical write operation. It hit on data block number 10, which resides on disk 0, okay, this one. So this is a random write that hit on disk block 10, okay? So that translates into multiple physical small IOs. Okay, so the first physical operation, so the first physical operation is it read block 10 out to memory. Okay, so this is keep in mind, this is the first physical read, a physical small IO. Okay. At the same time, because we're talking about parity chunk as well, and its associated parity chunk 10, data chunk 10's associated parity chunk is stored under disk number 2, which is P2, right, over here. Because in order to update this parity data, the parity chunk, you need to read it out. So this is the second physical operation, okay? Read the parity chunk out. And then don't forget to update your data, because this is we're talking about a logical RAID operation up front. So this is the third physical RAID operation. So this is the third operation, which is the blue-colored RAID operation. And what's the next? Of course, it's the update to the parity chunk accordingly, right? Because we're talking about RAID-5, and its data chunk 10's parity chunk is stored under disk 2. So here we're talking about disk 2. So that translated into the fourth physical operation, okay? Which is the update the new parity onto the disk, which is disk number 2. So what does it all mean? It means that for a single random RAID operation, it translates one single logical random RAID operations translated into 4 physical small IOs, okay? So that is only for one single logical RAID, okay? So considering we're talking about like random concurrently served small IOs, so that effectively boils down to n times r, right? Because we're talking about a total number of n disks. In this case, n is equal to 5. 5 times r divided by a factor. The factor is how much? It's 4, right? So this is a decreasing factor because because of this policy, one logical random RAID gets translated into 4 physical small IOs. So that is why we have this factor of 4. So this is all about like stochastic kind of probability theory, okay? So this slide gives a more detailed explanation. So the performance reasoning process is over here. So generally speaking, for a large number of random IOs, random read and write, RAID-5, sorry, is able to support keep all disks busy. So this is for random read, which is n times r. But for random write, which is shown at the second paragraph, the second statement, each random write generates 4 physical small IO operations. So that is why by keeping all disks busy, you further divide this all disk busy results by a factor of 4, which is n times r divided by 4. Okay, so this is why for disk 5, it's able to at least improve the random write throughput from, recall that it's r divided by 2 to n times r divided by 4, okay? So if you're talking about a random, a disk configuration of 5, so this is 5r divided by 4. 5 divided by 4 is obviously larger than one second, okay? So that means it's a slight improvement in terms of random write performance, okay? If the total number of disks is 5. Okay, so that's why we come up with this theoretical value, the modeling. This is whole modeling process, okay? And definitely read the textbook. It provides a more detailed analysis, the whole performance reasoning process. So the rest of this video is about this higher level summary, which we have basically been covering earlier. Okay, so I'm just gonna skip through. And the last slide. I'll definitely suggest all you guys to go through the textbook and have a deeper understanding about this RAID configuration, because RAID is important. It's just a piece of fascinating, beautifully designed software artifact. So definitely read the chapter. And that's it.